Hello, everyone. I'm Kyung-San Min. I'm working in Jeonbuk National University, and my expertise is endodontics. Today, I'm going to talk about hydraulic bioceramic material used in endodontics. I'll give two presentations. Part one is about introduction of the hydraulic bioceramic material, including its brief development history, related terminology, and general characteristics. In part two, I'm gonna show you the clinical application of this material. In 1993, around 30 years ago, a scientific article was published in Journal of Endodontics, one of the most famous journals in the endodontic field. This article was written by Mahmoud Turabinejad. Please remember the name. The topic was about introducing a new perforation repair material and comparing it with other conventional materials such as amalgam and intermediate restorative material. The name of the new material was MTA, and the result indicated that it shows a significantly better sealing effect compared to other tested material. At this time, the terminology sounds a little bit strange, but it gained lots of attention from dentists. In 1995, a US patent for the material was approved, and MTA is then ready to be used clinically. MTA stands for mineral trioxide aggregate. In fact, it is not scientific terminology, but chemically, we call this material calcium silicate-based cement because the base material of the cement consists of calcium silicate. This calcium silicate-based material was developed by Dr. Mahmoud Turabinejad, the author of the article, working in Loma Linda University, California. Although it is not scientific terminology, MTA still implies very important meaning in itself. Among the three words, trioxide should be remembered. According to Greek, tri means three in English. So trioxide means this material contains three oxides. The first one is calcium oxide, so-called lime, and the second one is silicon oxide, so-called silica. If they are reacted, calcium silicate can be produced, and it is the Portland cement, the building material. Also, the last one is bismuth oxide, the heavy metal. It should be added to provide radiopacity. Actually, the radiopacity is necessary to be used as an endodontic material because we need to distinguish the materials from adjacent to tooth structures in radiographic images. In fact, Dr. Turabinejad is not the first person who used the Portland cement for endodontic purpose. Surprisingly, in 1878, according to a literature, it was reported that a German dentist, Witte, used the Portland cement for root canal filling. However, we cannot find the result of the case. Anyway, the history of Portland cement in endodontic field is very long. Now, I think I need to explain the history of Portland cement shortly. In 1824, an English bricklayer, Joseph Aspdin, developed a method for producing a fast set cement and got the patent regarding it. He reacted lime and silica in furnace and obtained an aggregation of phases. Actually, it is calcium silicate, and it can set quickly after mixing with water. Interestingly, the hydrated final product looked like stones found in Portland Island in England. So, people began to call this material Portland cement, and we still use this terminology in concrete science. I would like to show you my interesting experiment done more than 15 years ago, which shows the excellent biocompatibility of Portland cement. In this experiment, I cultured human dental pulp cells on Portland cement, glass ionomer, IRM, and calcium hydroxide. If you take a look at the same image A, the cells on the Portland cement grow well, attached well, and shows numerous cytoplasmic extensions. This means that the cells are viable and the material is not cytotoxic. However, the cells on the other materials look like small round balls. This indicates the cells are dead and the material is not biocompatible. So I noticed that the Portland cement is very biocompatible than I expected. If you take a look at this short video, you can find how to mix the Portland cement with water calcite. The cement powder is mixed with water and then calcium silicate hydrate. The final product is produced. Historically, before the Portland cement was used, it took a long time for mankind to build architecture because pozzolan cement was used, which is a mixture of lime and volcanic ash. For example, it took around 10 years for building the Colosseum in Rome. However, thanks to the Portland cement, now we can construct the architectures very quickly. In this slide, you can see the pozzolanic reaction with chemical reaction formula. Briefly, slaked lime and silica undergo pozzolanic reaction, and eventually the same final product, calcium silicate hydrate, is produced. But the reaction is very slow, and it is the difference compared to Portland cement. Finally, Dentsply Tulsa launched ProRoot MTA in late 1990s. At this time, the color of the cement was gray, so clinicians call this gray MTA. But shortly after, white MTA was also launched to enhance the color. MTA gained lots of attention from many dentists because it shows favorable sealing ability even in the presence of moisture such as blood. Furthermore, it shows extremely high biocompatibility compared to other materials, as I shown before. However, it also possesses some drawbacks, including poor handling properties, long setting time, and tooth discoloration. Among these, the discoloration effect limits its application to the anterior teeth. Therefore, researchers tried to find the cause of the discoloration and finally found it shortly. Researchers demonstrated that bismuth oxide, the radiopacifier, was responsible for it. Bismuth oxide is a highly water-soluble heavy metal, and it can be bound with collagen fibers in dentin matrix easily. Consequently, it produces dark-colored dentin structure. After that, researchers tried to find alternatives of bismuth oxide. The most frequently used radiopacifier is now zirconium oxide. It is white-colored and does not discolor the tooth structure anymore. However, the atomic weight of zirconium oxide is quite low compared to bismuth oxide. So it should be added much more in the powder. In some constants, it possesses more than 50% of the whole powder weight. Now, can we still call this material calcium silicate-based one? I don't think so. Therefore, we need to find a more suitable terminology. Researchers began to call it hydraulic cement because it is mixed with water. As you know, etymologically, hydro means water in Greek. But this term is usually used in concrete science and not suitable for medical science alone. Researchers also call this type of material bioceramic. Bioceramic indicates a class of materials which is biocompatible and consequently used for repairing or replacing damaged hard tissue, such as bone, tooth, something like that. Now, let me summarize the definition of each terminology. Mineral trioxide aggregate is a cement formulated from Portland cement combined with bismuth oxide powder. Calcium silicate is a group of compounds which can be produced by reacting calcium oxide and silicon oxide in various ratios. Hydraulic cement are inorganic materials that have the ability to react with water under ambient conditions to form a hardened and water-resistant product. Bioceramics are ceramic materials that are biocompatible and used in many types of medical procedures. Among these words, we can consider hydraulic bioceramics as the most appropriate terminology, as I suggested. However, it still has one more problem to be used clinically. That is the poor handling property, as I mentioned before. So, clinicians often use specially designed equipment to facilitate the delivery of the cement. For example, when clinicians feel the root end cavity, a manual plugger is used. As you see, a Teflon tube is assembled with the plugger and the mixture cement is put into the empty space as shown in the pictures. As you may expect it, this procedure is very tricky and well-trained assistance is required. Also, if the repair site is located deeper, another specially designed instrument is necessary. It is hard to handle and expensive as you expected. Consequently, to facilitate the delivery of the material into the small site space, such as tooth or root canal or onto the pulp, it would be much better provide flowability and injectability like paste-type intracanal medicament. Around 10 years ago, manufacturers mixed the powder with non-aqueous vehicles such as polyethylene glycol and propylene glycol and placed it in a watertight syringe to prevent unexpected hydraulic setting. As you know, if it is mixed with water, it will be set before the use. Now, we can call this type of material pre-mixed or injectable, and it is very useful for application even into the very small space such as root canal system. Here, I introduced a brief history of the endodontic bioceramics and summarized the terminology. I hope it helps you with understanding the useful material. And next time, I'll introduce the clinical application of the hydraulic bioceramics, especially in endodontic treatment. Thanks for watching my presentation and hopefully see you guys again in part 2, the clinical application of the hydraulic bioceramic materials, especially in various endodontic cases. You can see many clinical photos and videos for sure. Bye.